The sun looks eternal from Earth, a steady golden presence rising over oceans, cities, and sleeping continents. But deep inside its core, a silent countdown has already begun. Hydrogen is disappearing, helium is gathering, and with every passing billion years, the star that gives Earth life grows brighter, hotter, and more dangerous. Long before the sun becomes a red giant, the oceans will fade, the atmosphere will change, and the blue planet may become a dry world of stone. Then the sun will swell, shed its outer layers, and leave behind a white dwarf cooling through almost endless darkness. If this journey into the far future sparks a sense of wonder, a like subscription or share helps more quiet science stories reach curious minds. Thank you sincerely for spending this time here. What time is it where this is playing, and where in the world are these words being heard? Leave a comment below. Now, let the final life of the sun begin. The sun appears permanent because every human life unfolds beneath the same dependable rhythm of dawn and dusk. Yet its calm face hides a process that is always moving toward change. It is a star in the long middle portion of its existence, neither newly born nor close to its final collapse, and for now it holds itself in a balance so precise that the planets can circle it for ages, while life persists on one small world. At the centre, gravity pulls inward with enormous force, pressing the sun's material toward a dense and superheated core. Against that inward pull, energy produced by nuclear fusion pushes outward. The two forces oppose one another without either fully winning. This condition, known as hydrostatic equilibrium, gives the sun its present stability. It does not mean the sun is inactive. It means its violence is contained within a structure that constantly adjusts. Every second, vast amounts of hydrogen in the core are transformed into helium. The process does not burn in the ordinary sense. There is no flame and no oxygen-fed fire. Instead, hydrogen nuclei are forced close enough together by extreme heat and pressure that they combine through a chain of reactions. A small amount of mass disappears in the process, converted into energy according to the relationship between mass and energy, described by modern physics. That energy begins a difficult journey outward, first through the dense interior and eventually into space as light and heat. By the time sunlight reaches Earth, it has crossed roughly 150 million kilometers in a little over 8 minutes. But the energy carried by that light may have spent far longer trapped inside the sun, repeatedly absorbed and re-emitted through its inner layers before finally escaping from the visible surface. This long delay gives the sun an unusual kind of memory. The light arriving at Earth reflects conditions at the surface only minutes earlier. Yet the energy beneath it began deep in the core on timescales far older than any civilization. The sun's visible surface, called the photosphere, has an average temperature of several thousand degrees, while the core reaches many millions of degrees. Between them lies a layered interior shaped by different forms of energy transport. In the radiative zone, energy moves outward mainly through the repeated interaction of light with matter. In the convective zone above it, hot plasma rises, cools, and sinks in broad currents. These motions help create the restless texture seen across the solar surface, where bright cells constantly shift and vanish. Even in its most stable age, the sun is never still. Its magnetic field twists through electrically charged plasma, producing sunspots, flares, prominences, and vast eruptions known as coronal mass ejections. Some of these events send clouds of charged particles across the solar system when they reach Earth. The planet's magnetic field and atmosphere absorb much of their force, sometimes producing auroras near the poles. Stronger events can disturb satellites, radio communication, navigation systems, and electrical grids. These hazards reveal that the sun's life-giving role has always existed beside a capacity for disruption. The same star that powers photosynthesis and drives weather can also strike technological systems with waves of energy and charged matter. Yet these outbursts are temporary expressions of the sun's magnetic behavior. They are not the central reason the sun will one day become dangerous to Earth. The deeper change is quieter, slower, and impossible to stop. The core is gradually altering its own composition. Hydrogen is being used, helium is accumulating, and the structure of the sun is responding. This transformation happens so slowly that it cannot be noticed across a single lifetime, or even across the span of recorded history. It becomes visible only when the sun is understood as one member of a much larger population of stars. Across the galaxy, astronomers observe stars at many different ages. Some are forming inside cold clouds of gas and dust. Some shine in stable middle age. Others have swollen into red giants, shed their outer layers, or collapsed into dense stellar remnants. No observer needs to watch one star from birth to death. The sky contains examples of many stages at once, allowing the sun's future to be reconstructed from the behavior of similar stars and from physical models tested against observation. The sun formed about 4.5 billion years ago from part of a large molecular cloud. Gravity drew gas and dust inward, and as the material contracted, the central region became hotter and denser. When conditions were finally extreme enough for hydrogen fusion to begin, a new star entered a long period of stability. The remaining material around it flattened into a disk and gradually formed the planets, moons, asteroids, and smaller bodies of the solar system. Earth emerged within a region where liquid water could remain on the surface for long periods. This position alone did not guarantee life, but it created a setting where life could develop and endure. The sun supplied the steady flow of energy that shaped climates, drove the water cycle, and supported the chemistry of living systems. In that sense, life on Earth is not separate from the sun's history. It is one consequence of a temporary phase in the life of a star. Temporary, however, does not mean brief. The sun's stable hydrogen-burning stage lasts for billions of years. By stellar standards, this is an era of remarkable calm. The sun has already spent much of its life in this phase and is expected to remain in it for billions of years more. Human existence occupies only a vanishingly small fraction of that span. Entire species rise and disappear while the sun changes almost imperceptibly. Continents drift, oceans open and close, climates shift, and mass extinctions reshape life. Yet the sun continues to look nearly the same. Its apparent constancy creates the illusion that the conditions supporting Earth are fixed. They are not. Fusion slowly changes the core, and that change causes the sun to brighten over time. A young sun shines less intensely than the sun does now. Geological evidence shows that Earth nevertheless maintained liquid water early in its history, creating a puzzle often called the faint young sun problem. Explanations involve the composition of the ancient atmosphere, stronger greenhouse warming, differences in clouds, and other factors that help the planet retain heat under a dimmer star. The puzzle itself points toward an essential fact: the sun has not always had its present brightness, and it will not keep it. As helium accumulates, the core becomes denser. Gravity compresses it more strongly, raising the temperature and increasing the rate of fusion in the surrounding hydrogen-rich regions. The sun responds by producing more energy. This is the hidden clock inside its apparent stillness. It does not tick in seconds or years, but in hundreds of millions of years. Each slow adjustment makes the star slightly more luminous. For most of its history, the effect is gentle enough for Earth's climate system to absorb through changes in the atmosphere, oceans, and carbon cycle. But those systems have limits. The same increase in brightness that is barely noticeable across an age eventually becomes large enough to transform the planet. Long before the sun becomes a red giant, long before its outer layers swell toward the inner planets, its gradual brightening begins to threaten the conditions that complex life depends upon. The danger, therefore, does not arrive as a sudden stellar catastrophe. It begins as a nearly invisible trend embedded in the sun's normal operation. Every stable day is powered by the process that also leads toward instability. Every sunrise is evidence of a star successfully resisting gravity, and also of a core that is slowly exhausting the fuel maintaining that resistance. The sun is not dying now in any immediate sense. It remains a middle-aged star with an immense future ahead. But its present balance is not a permanent state. It is a stage, and every stage in stellar evolution contains the conditions of the one that follows. The sun's story is therefore not a movement from life into death at a single moment. It is a long transformation in which stability gradually changes its meaning. The star that supports Earth today becomes brighter because it continues to function exactly as a healthy star should. Its danger comes not from failure, but from success sustained across deep time. Hidden beneath the familiar light, helium gathers, pressure shifts, and the future begins in silence. The sun's apparent calm depends on a core that is never truly at rest. Deep beneath the visible surface, where pressure is so great that matter behaves as a dense plasma, hydrogen continues to fuse into helium, and every successful reaction changes the balance that made the reaction possible. The transformation is gradual, but it is irreversible. Hydrogen nuclei are consumed, helium nuclei remain behind, and the central region becomes richer in a substance that does not yet take part in the same fusion process. Helium can fuse under hotter conditions, but the present core is not hot enough for that stage. For now, it accumulates like ash in a furnace, though it is not cold or inert in any ordinary sense. It remains trapped in a realm of immense heat, contributing mass and pressure while no longer serving as the primary fuel. This growing helium core is the quiet record of the sun's age. Every particle of helium marks energy already released, light already sent outward, and hydrogen that can never be restored. The sun contains enough hydrogen to continue for billions of years. Yet the useful fuel is not spread evenly through the entire star. Fusion occurs mainly in the central region, where temperature and pressure are highest. Hydrogen in the outer layers remains largely untouched, but the core cannot simply reach outward and draw all of it inward. The sun is not mixed from center to surface as a single boiling body. Its interior is layered, and those layers limit how material circulates. This means the star's future is determined not only by how much hydrogen it contains, but by how much hydrogen is available where fusion can happen. As helium gathers, the average particle arrangement in the core changes. A helium nucleus is heavier than a hydrogen nucleus, and the increasing concentration of helium affects the relationship between pressure, density, and temperature. The core slowly contracts under gravity. Compression raises its temperature, and the hotter environment causes the remaining hydrogen to fuse more rapidly. The sun therefore does not fade as its hydrogen is used. It becomes brighter. This seems almost paradoxical. A machine running low on fuel might be expected to weaken, but a star is governed by gravity, and gravity responds to any loss of pressure by squeezing the interior more strongly. The contraction releases additional heat. The higher temperature accelerates fusion. Greater fusion restores the outward pressure needed to hold the star up. A new balance forms, but it is not the same balance as before. It operates at a slightly higher temperature and produces a slightly greater flow of energy. The sun adjusts to the changing core by shining more intensely. This self-correcting behavior allows it to remain stable for an extraordinary length of time, yet each correction moves it farther from its original state. The process resembles a staircase with steps so broad that entire geological eras pass before the next rise becomes obvious. Early in the sun's life, the core contains more hydrogen and less helium. It is cooler and less compressed than it is now. The young sun shines with only part of its present luminosity. Over billions of years, helium accumulation drives the core toward higher density and temperature, and the star's brightness increases by a substantial fraction. Earth's climate and atmosphere respond throughout this slow brightening. The planet is not a passive stone receiving a fixed amount of light. Its oceans, rocks, living organisms, clouds, and gases exchange energy and carbon in ways that can soften long-term changes. Silicate rocks react with carbon dioxide through weathering. Carbon is carried into the oceans and eventually stored in sediments. Volcanic activity returns some of it to the atmosphere. This long carbon cycle acts as a stabilizing influence, helping Earth avoid the full effect of a gradually changing sun. When the planet warms, chemical weathering can speed up and draw more carbon dioxide from the air, weakening the greenhouse effect. When the planet cools, weathering can slow, allowing volcanic carbon dioxide to build and restore warmth. This feedback has helped maintain liquid water across immense spans of time, yet it cannot resist the sun forever. As solar energy rises, the climate system must remove more carbon dioxide to keep temperatures within a habitable range. Eventually, the atmosphere becomes too poor in carbon dioxide for many plants to survive. Long before the oceans boil away, the foundation of complex ecosystems begins to weaken. The future danger is therefore linked directly to the same core chemistry that now appears remote from the surface. A change among atomic nuclei deep inside the sun eventually reaches forests, oceans, and living cells across the distance of space. The connection unfolds slowly, but it is exact. More helium means a denser core. A denser core means stronger compression. Stronger compression means greater heat. Greater heat means faster hydrogen fusion. Faster fusion means higher luminosity. Higher luminosity means a warmer Earth and increasing stress on the mechanisms that preserve habitability. No single moment marks the beginning of this chain because it has already begun. It begins with the first fusion reactions after the sun's birth and continues through every era that follows. The present sun is brighter than the young sun, and the future sun will be brighter still. Astronomers understand this progression through models of stellar structure and through observations of stars with similar mass but different ages. Stars of roughly the sun's mass follow a broadly predictable path because the same physical laws govern their interiors. Their exact histories differ according to composition, rotation, magnetic behavior, and surrounding environment. But the central pattern remains. Hydrogen fusion creates helium. Helium changes the core. The changing core alters the whole star. These models are tested by measuring stellar brightness, temperature, mass, chemical composition, and oscillations. The sun itself vibrates in many overlapping patterns, and those vibrations carry information from its interior. The study of these waves, known as helioseismology, allows scientists to infer the sun's internal density, rotation, and structure with remarkable precision. The surface trembles in response to waves moving through the star, much as seismic waves reveal the hidden layers of Earth. These observations confirm that the sun is not uniform. Its core, radiative region, convective region, and outer atmosphere each behave differently, and the boundaries between them influence how energy and magnetic fields move. Heliosismology also reveals the accumulated effects of the Sun's long life. The present internal structure matches a star that has spent billions of years converting hydrogen into helium. The evidence of age is therefore not limited to ancient meteorites or models of planetary formation. It is written into the Sun's own vibrations. Even so, the slow pace of stellar evolution makes the change difficult to imagine. Across a human lifetime, the Sun's luminosity does not rise in a way that can be felt directly. Short-term variations caused by the solar cycle, sunspots, and magnetic activity are far more noticeable, but these are small fluctuations around a long upward trend. The core's evolution is quieter than any storm. It does not announce itself with a flare or darken the sky with an eruption. It works beneath the surface through pressure, density, and time. The Sun remains almost the same shape and colour, while its centre gradually becomes a different place. Hydrogen grows scarcer in the deepest region. Helium becomes dominant. The temperature climbs. Fusion shifts outward into a broader area around the helium-rich centre. The star continues to support itself, but the location and intensity of its energy production slowly change. Eventually, central hydrogen becomes so depleted that the Sun can no longer maintain its existing structure through the same pattern of fusion. That crisis lies billions of years ahead, but its cause is already present. The future red giant is not created by a sudden external event. It grows from the helium now collecting at the centre. Every sunrise adds an almost immeasurable amount to that hidden core. Every age of Earth passes under a star that is quietly remaking itself from within. The Sun appears steady because its adjustments are slow, not because its condition is fixed. Its balance is dynamic, renewed at each stage by contraction and heat. For now, this mechanism protects the solar system from abrupt change. Over deep time, it guarantees that change will come. The Sun's middle age is therefore not a pause between birth and death. It is the long engine of transformation, and the helium gathering in darkness is the first clear shape of the ending to come. The Sun does not need to become a red giant before it begins to remake Earth. Its danger arrives much earlier, carried by a slow increase in brightness that unfolds across hundreds of millions of years. The change is too gradual for any single generation to notice, yet it is relentless. As helium continues to gather in the core, gravity compresses the central region, the temperature rises, and hydrogen fusion becomes more intense. The Sun responds by releasing more energy into space. At first, Earth absorbs this increase through the familiar mechanisms of climate. Clouds shift, oceans store heat, rocks draw carbon dioxide from the air, and living systems adapt to changing environments. These responses create the appearance of resilience. Across deep time, they have already helped the planet survive a sun that has grown brighter since its youth. But resilience is not the same as permanence. Each stabilizing process works only within a limited range, and the rising solar output steadily pushes Earth toward the edge of that range. The first great transformation is not a sudden boiling of the oceans or a wall of fire sweeping across continents. It is a slow weakening of the systems that regulate temperature and support photosynthesis. As the surface warms, rainfall increases in many regions, chemical weathering accelerates, and more carbon dioxide is removed from the atmosphere. This reduction can cool the planet by weakening the greenhouse effect. But it also creates a biological problem. Plants depend on carbon dioxide as a raw material for photosynthesis. If the concentration falls too far, many forms of plant life can no longer maintain their metabolism. Some plants use more efficient pathways and may survive longer, but even they face limits. Forests shrink, grasslands thin, and ecosystems lose the primary producers that capture sunlight and turn it into chemical energy. Animals do not disappear because the sun suddenly burns them. They disappear because the food webs beneath them become simpler, poorer, and less stable. The decline begins quietly, one habitat at a time, while the star overhead still looks familiar. The sun's visible disk remains nearly unchanged to any observer living through one brief era. Its colour does not announce the future. Its warmth increases by increments spread over such immense spans that the change becomes obvious only through models of stellar evolution and the geological record of planetary response. Yet the consequences accumulate. Warmer air holds more water vapour, and water vapour itself is a greenhouse gas. This creates a feedback. More solar energy warms the surface. Warmer oceans release more vapour into the atmosphere. More vapour traps additional heat. At first, rainfall and weathering may still help stabilise the climate, but eventually the rising moisture begins to overpower those protections. The upper atmosphere becomes wetter. There, sunlight breaks water molecules apart. Hydrogen, being light, escapes into space. Oxygen may react with surface rocks or remain temporarily in the atmosphere, but the lost hydrogen cannot easily return. Earth begins to lose water not only from the surface but from the planet itself. This process develops long before the oceans vanish completely. Seas retreat from shallow margins. Inland waters disappear, dry regions widen. The planet's blue surface becomes less continuous as coastlines move and continents expand beneath a hotter sky. Life follows the remaining water, concentrating in cooler regions, at higher latitudes, underground, or in isolated environments where liquid water persists. The biosphere becomes more fragile because it occupies less space and depends on fewer refuges. Complex organisms, with their greater energy demands and narrower environmental tolerances, are likely to face severe pressure before simpler life does. Microbial communities may endure in places where plants and animals cannot, continuing in deep rock beneath the ground, or near the last stable bodies of water. The end of habitability is therefore not a single event. It is a long retreat from complexity toward endurance, from open landscapes toward hidden shelters, and from a rich global biosphere towards scattered pockets of survival. The sun remains the source of all the energy driving this transformation. The same photons that once supported abundant life now arrive in greater numbers, not because the star has become hostile in any conscious sense, but because its internal balance has evolved. This distinction gives the future a quiet severity. Nothing goes wrong inside the sun. The star follows the normal path of a stable star of its mass. Earth becomes endangered because a planet suitable for life during one stellar age may not remain suitable during the next. Habitability is a moving relationship between a world and its star. The region where liquid water can persist, often called the habitable zone, shifts outward as the sun brightens. Earth currently lies within that zone, but the zone does not remain fixed around the same orbit. Over time, the inner edge moves beyond Earth. A world once placed at a favourable distance becomes too close, even though its orbit changes little. Farther out, colder worlds receive more heat. Mars may briefly experience conditions less severe than those of its present surface, while icy moons in the outer solar system may warm. These changes do not guarantee new living worlds. Atmospheres, gravity, chemistry, radiation, and internal geology all matter. Still, the migration of the habitable zone shows that the sun's aging does not merely destroy one environment. It reorganizes the thermal structure of the entire solar system. Regions now frozen may thaw, regions now temperate may dry. The solar system's geography of possibility slowly moves away from the star, on Earth. The progression toward greater heat affects every major cycle. Evaporation strengthens. Weather patterns become more extreme. The oceans absorb heat until they can no longer buffer the surface effectively. Ice disappears, reducing the amount of sunlight reflected into space. Darker land and water absorb more energy, adding another warming feedback. Carbon stored in soils and rocks may return to the atmosphere under some conditions, while other processes continue to remove it. The exact path is complex, and the timing depends on interactions among the atmosphere, oceans, continents, and living organisms. Scientific estimates therefore differ in detail, yet the broad direction is secure. A brighter sun raises Earth's temperature and eventually overwhelms the systems that have maintained surface water and complex life. The uncertainty concerns how quickly each threshold arrives, not whether the underlying trend exists. Long before the red giant stage, Earth becomes a harsher planet. The future surface may pass through intervals that resemble the hottest deserts of the present, but such comparisons remain incomplete. Modern deserts still exist within a world of oceans, weather, biological cycles, and breathable air. The later Earth loses those global supports. Deserts no longer sit at the margins of fertile regions. They become the dominant landscape. Rivers weaken as rainfall patterns fail. Lakes contract into mineral basins. Soil loses organic structure. Winds carry dust across continents stripped of vegetation. The atmosphere changes as photosynthesis declines and water escapes. The planet that once appeared blue and white from space becomes increasingly brown, pale, and clouded by heat. No single boundary separates a living Earth from a dead one. Instead, the biosphere narrows across ages. Some organisms vanish early. Others persist through adaptations that are impossible to predict in detail. Evolution may produce forms suited to higher temperatures, lower carbon dioxide, and more limited water. But adaptation cannot overcome the loss of the basic physical conditions life requires. Once liquid water becomes unstable across most of the surface, the possibilities contract sharply. Once the oceans enter a runaway decline, even the deepest refuges become temporary. The approaching crisis remains slow by human standards, yet rapid compared with the full history of the Sun. 1 billion years is vast beside civilization, but only a fraction of a star's life. The Sun can still appear middle-aged while Earth is already passing beyond habitability. This is one of the most important features of the solar future. The death of the biosphere and the death of the star are separated by an enormous interval. Earth does not wait for the Sun's final transformation. It is undone during the long approach. By the time the Sun begins to swell dramatically, much of the planet's living history is already over. The brighter Sun therefore marks the first true stage of the ending, not because it destroys Earth at once, but because it closes the climate window within which complex life can persist. The light remains golden, the days continue, the star still rises over the horizon. Yet beneath that familiar appearance, the balance between Earth and Sun shifts beyond recovery, and the warmth that once opened the way for life begins, with almost perfect patience to take that way away. The decline of Earth's biosphere does not begin with a final burst of heat. It begins with a narrowing of possibilities. As the Sun grows brighter, the planet's climate systems continue to adjust, but each adjustment demands a greater sacrifice. Carbon dioxide is steadily removed from the atmosphere as warmer conditions accelerate the weathering of exposed rock. Rainwater absorbs carbon dioxide and forms a weak acid. That water reacts with minerals, carrying dissolved material into rivers and oceans, where carbon can become locked into sediments. Over immense spans, tectonic activity and volcanism return some of that carbon to the air, creating a cycle that has helped regulate Earth's temperature. In the distant future, however, the balance shifts. The brighter sun adds more heat, so the climate system must draw down more carbon dioxide to prevent even stronger warming. The greenhouse effect weakens. But the atmosphere also becomes less useful to the organisms that depend on carbon dioxide for photosynthesis. Plants are among the first great pillars of the biosphere to feel this pressure. They do not vanish all at once. Different groups respond at different rates because they use different chemical pathways to capture carbon. Some plants can continue photosynthesis at lower carbon dioxide levels than others. Those better adapted forms may spread for a time as forests thin and less efficient species retreat. Yet even the most resilient plants face a lower limit. As carbon dioxide falls, the energy cost of collecting it rises, growth slows, and reproduction becomes more difficult. Landscapes that once carried dense vegetation begin to open. Forest canopies break apart. Grasslands become sparse, wetlands contract. The change is biological, but it is also physical. Roots no longer hold soil together as effectively. Organic matter declines. Water runs across bare surfaces more quickly, carrying nutrients away. Dust becomes more common in the atmosphere, and the ground loses the living structure built by fungi, microbes, roots, and decaying tissue. The biosphere is not merely a collection of organisms placed on a planet. It is a network that helps create the conditions in which its members survive. Plants release water vapor, shape local rainfall, cool the surface through evaporation, build soil, store carbon, and provide food. When plants decline, those functions weaken together. A hotter world becomes even harder to stabilize because the living systems that once softened heat are disappearing. Animals follow this change through the food web. Herbivores lose both quantity and variety of food. Populations become smaller and more isolated. Predators decline afterward because prey becomes scarce. Species that depend on complex habitats vanish as those habitats simplify. Forest animals cannot survive where forests have become scattered groves. River species cannot persist where rivers flow only seasonally. Coastal ecosystems weaken as evaporation changes salinity and sea levels retreat from shallow shelves. The collapse moves upward and outward, but it begins at the base, where sunlight can no longer be turned into enough usable chemical energy. In the oceans, microscopic photosynthetic organisms face their own limits. Phytoplankton form the foundation of many marine food webs and contribute greatly to the production of oxygen. They depend on light, nutrients, carbon dioxide, and a stable range of temperatures. As the oceans warm, their layers become more sharply separated. Warm surface water mixes less easily with colder water below, so nutrients from the depths reach the sunlit upper zone less efficiently. Some regions may become biologically poor, even while liquid water still covers much of the planet. Marine productivity declines. Fish, larger plankton, and ocean predators lose the food supply beneath them. Coral reefs and other sensitive communities disappear early, but even hardy ecosystems eventually contract as heat, acidity, oxygen loss, and nutrient scarcity combine. The atmosphere changes slowly in response. Oxygen does not vanish as soon as plants begin to decline because the air contains an enormous reservoir, and geological processes also affect its abundance. Yet photosynthesis is the principal long-term source that replenishes free oxygen. As land plants and marine microorganisms fade, less oxygen is added. At the same time, oxygen continues to be consumed through respiration, decay, chemical reactions with rocks, and volcanic gases. The balance turns downward. Across long ages, the atmosphere becomes less supportive of large, active animals. Creatures with high energy demands are especially vulnerable because their bodies require a steady supply of oxygen to maintain movement, temperature, and complex organs. Smaller organisms with slower metabolisms may persist longer. Anaerobic microbes, which do not depend on oxygen, may expand into environments where more complex life can no longer function. Earth's living world begins to resemble its ancient past, not because time reverses, but because the conditions that once allowed complex life to flourish are being withdrawn. The great diversity of animals, plants, and fungi gives way to simpler communities capable of surviving heat, dryness, low oxygen, and chemical stress. Evolution continues throughout the decline. It does not stop when conditions become harsh. New adaptations appear, and some lineages may endure far beyond expectations. Organisms can become more efficient at using water, shelter beneath the ground, shift their active cycles toward cooler periods, or form partnerships that reduce the cost of gathering nutrients. Microbes can inhabit cracks in rock, salty pools, deep sediments, and pores far below the surface. These refuges may remain stable after open landscapes become nearly sterile. Yet evolution can work only with environments that still provide energy, liquid water, and usable chemistry. It cannot preserve a forest after the climate no longer permits trees to grow. It cannot sustain an oceanic food web after circulation and nutrients have failed. Adaptation delays the end for particular forms of life, but it does not cancel the planetary trend. The decline is made more severe by feedbacks between life and climate. Fewer plants mean less evaporation from leaves and less cloud formation over some regions. Fewer clouds can allow more sunlight to reach the ground. Bare soil and exposed rock may absorb heat differently from vegetated land. Wildfires, while oxygen remains abundant enough to support them, release stored carbon and remove habitats faster than they can recover. Later, as oxygen falls and vegetation becomes sparse, even fire becomes less common, leaving a quieter world of dry mineral surfaces. The sounds and motions associated with complex ecosystems fade. Seasonal migrations cease. Pollination networks collapse. Rivers no longer carry the same burden of leaves, wood, and organic matter toward the sea. The planet becomes geologically active but biologically subdued. This transformation takes place over timescales so long that each surviving ecosystem may appear stable within its own brief age. A species may evolve, spread, and disappear while the solar brightness changes only slightly. The full decline becomes visible only when these ages are placed beside one another. What seems like a series of local extinctions and climate shifts is part of a single stellar-driven movement. The Sun continues to convert hydrogen into helium, and that distant nuclear change governs the shrinking future of life. Complex life likely disappears long before the last microbes. Animals dependent on plants and oxygen face the earliest irreversible losses. Plants persist in reduced forms until carbon dioxide becomes too scarce. Photosynthetic microbes may survive in specialized environments after most surface vegetation is gone. Eventually, heat and water loss push even microbial life toward isolated underground refuges. In those hidden places, life may continue without forests, oceans, or open skies, sustained by chemical energy and small traces of water. The biosphere that once covered continents and filled seas becomes a thin, fragmented presence beneath a hostile surface. Its final stages may be difficult to recognize from afar. Earth could still carry an atmosphere and patches of cloud while almost all complex life has vanished. The planet would remain in orbit, still receiving sunlight, still turning through day and night, but the living systems that once transformed its surface would be nearly silent. There is no single last day for the biosphere. One valley may remain green after entire continents have dried. One deep aquifer may shelter microbes after the surface has become sterile. The end advances unevenly, following altitude, latitude, rock chemistry, and the last movements of water. For a long time, survival becomes a matter of place. The long decline reveals that extinction on a planetary scale need not arrive through impact, eruption, or sudden darkness. It can emerge from an ordinary star growing brighter by the slow laws of its own interior. The sun gives life enough time to become complex, and then, by continuing to age, gradually removes the conditions that complexity requires. The oceans do not vanish in a single convulsion. They retreat through a sequence of thresholds, each one making the next more difficult to avoid. As the sun continues to brighten, more heat reaches Earth's surface, and evaporation strengthens across every sea. At first, the planet still carries the familiar cycle of water rising into the atmosphere, condensing into clouds, and returning as rain. Yet a warmer atmosphere can hold more vapor, and that vapor traps additional heat. The cycle that once distributed water begins to amplify the warming that threatens it. More sunlight warms the oceans. Warmer oceans release more water vapor. More water vapor deepens the greenhouse effect. The surface heats further, and evaporation accelerates again. This feedback does not need to begin suddenly. It can grow quietly while coastlines change by small amounts across long ages. Shallow seas shrink. Salt marshes disappear. Continental interiors dry more deeply between storms. Rivers carry less water to the coasts, while high latitudes and high elevations become some of the last places where ice or seasonal snow can survive. The loss of surface water is accompanied by changes above the planet. In the present atmosphere, most water vapor remains in the lower layers, where temperatures fall with altitude and much of the vapor condenses before it can climb higher. In a hotter future, the upper atmosphere becomes increasingly moist. Water molecules reach regions where intense ultraviolet light from the sun can break them apart. Oxygen remains behind or reacts with minerals, while hydrogen, the lightest element, can escape Earth's gravity and drift into space. Once this happens, the planet is no longer only moving water from ocean to cloud and back again. It is losing part of the water molecule permanently. The hydrogen that escapes cannot easily be recovered. Over immense spans, this leakage becomes one of the main paths by which Earth's oceans are reduced. The process resembles what likely happened on Venus. Though the histories of the two planets are not identical, Venus may once have held more water than it does now, but a powerful greenhouse state and long exposure to sunlight helped strip much of that water away. Earth begins from a cooler and more favourable condition, yet the aging sun steadily pushes it toward the same broad danger, an atmosphere rich in vapour, a surface unable to cool, and water broken apart faster than the planet can preserve it. The exact timing of each stage remains uncertain because clouds, atmospheric circulation, continents, and chemical cycles interact in complicated ways. Some clouds can reflect sunlight and delay warming. Others can trap heat. Changes in ocean currents can redistribute energy. Continents move, altering coastlines and rainfall. These details matter, but they do not reverse the long direction set by the sun's increasing luminosity. As the oceans diminish, their ability to buffer temperature also weakens. Water has a high capacity for storing heat, so the present oceans soften the difference between day and night, summer and winter, tropics and poles. A world with less ocean becomes more thermally extreme. Land heats quickly under daylight and cools more rapidly after sunset. Weather becomes less stable because the great reservoirs that once moved heat through currents are smaller. The atmosphere may still carry thick clouds for a time, but the surface beneath them grows more hostile. Rain can become intense in some regions even as the total supply of surface water declines. Storms erode exposed land, carve temporary channels, and leave mineral deposits behind when the water evaporates. Each remaining basin becomes saltier as fresh water escapes and dissolved minerals concentrate. Organisms that once lived in ordinary seawater are replaced by forms able to tolerate heat, salinity, and chemical stress. Eventually, even those communities fail. The deep ocean may persist longer than shallow seas because of its volume, but it cannot remain isolated from the warming above. Heat penetrates downward, circulation weakens, oxygen becomes scarce. Large marine animals disappear, followed by smaller and simpler organisms as food webs collapse. The last ocean ecosystems may exist near chemical energy sources on the seafloor or within protected sediments. Yet these refuges also depend on liquid water remaining stable. As evaporation continues, sea level falls across continental shelves and then into the deeper basins. Former coastlines become cliffs above dry plains. Mountain ranges once submerged beneath the sea stand exposed to the atmosphere. Layers of salt accumulate where entire bodies of water have vanished. The continents appear larger, but the planet is not gaining land in any living sense. It is losing the medium that connected climates, carried nutrients, and supported most of its biological productivity. The final seas may survive as scattered, superheated basins enclosed by high ground. They no longer resemble the blue oceans of the present. Their water is dense with dissolved minerals. Their surfaces may boil in the strongest heat, while deeper layers remain liquid under pressure for a time. Clouds rise from them and move across a world with little vegetation and almost no flowing fresh water. Rain falls onto hot rock, reacts with minerals, and evaporates before reaching distant basins. The global water cycle contracts into local loops that become shorter and less effective. Eventually, the remaining surface water is too limited to support a broad atmosphere of clouds and rain. The sky clears in places, allowing still more sunlight to reach the ground. The exposed surface darkens or brightens according to rock and salt, changing how much energy is absorbed. With little life left to alter the atmosphere, geology and radiation take over as the main forces shaping the planet's appearance. The last traces of life may persist below the surface, where porous rock holds water beyond the reach of direct sunlight. Deep aquifers, fractures, and mineral pores can shelter microbes from extreme heat for a while. Some may use chemical reactions rather than sunlight as their source of energy. Their world is small, dark, and isolated from the surface that once carried forests and seas. As geothermal heat rises from below and solar heat presses from above, the habitable layer narrows between them. Too close to the surface, water evaporates or becomes too hot, too deep. Pressure and internal heat make survival impossible. The final biosphere may be compressed into a thin shell within the crust, scattered across rare places where temperature and chemistry remain tolerable. Even there, the supply of water is finite. Rock can release some water through chemical reactions, and volcanic gases can add small amounts to the atmosphere. But these sources cannot rebuild global oceans while hydrogen continues to escape to space. The planet's inventory is being drained. In the far future, the surface crosses into a state where liquid water is no longer stable for long anywhere under ordinary pressure. Pools flash into vapor. Rain cannot reach the ground without disappearing. Any exposed ice passes directly into gas or melts and boils away. The atmosphere becomes thick with water vapor before much of that vapor is broken apart and lost. Oxygen produced by this splitting may briefly accumulate, but it does not signal life. Without continuous biological activity, oxygen can arise from the destruction of water itself. It reacts with iron and other minerals, altering the crust and leaving oxidized surfaces behind. the planet becomes dry not only in appearance but in composition. Its oceans are transformed into hydrogen lost to space and oxygen bound into rock or remaining in the air. From a distance, Earth no longer shines as a blue world. The colour of open water fades, cloud patterns thin, and the continents merge visually into a globe of stone, salt, and haze. The sun is still far from its red giant phase. It remains recognisably the same star, only brighter than before. This is what makes the loss of the oceans so profound. Earth becomes uninhabitable while the sun still appears stable. The end does not wait for the star to swell across the sky. It arrives through the patient accumulation of heat, the escape of hydrogen, and the failure of water to remain. Once the last oceans are gone, the planet has crossed a boundary that no natural climate cycle can undo. No hidden reservoir can restore the old seas on the scale required, and no ordinary geological pulse can replace the hydrogen already dispersed through interplanetary space. Rain, rivers, ice, and seas belong to the past. The surface continues to turn beneath daylight, but the world that water built has ended. By the time Earth's oceans are gone, survival can no longer mean preserving the planet as it once was. The surface has become a dry and overheated landscape. The atmosphere has changed, and the sun continues to brighten. Any descendants of humanity still existing in that distant age must depend on environments built deliberately against the conditions outside. The first possibility is not immediate escape to another star, but withdrawal into controlled habitats. Beneath the ground, thick layers of rock can shield living spaces from radiation and temperature extremes. Artificial systems can recycle air, water, and nutrients, while energy may come from solar power, nuclear reactions, or other technologies unavailable to the present. Such refuges could endure for a time, especially while the Earth still retains accessible materials and a predictable orbit. Yet they would not restore the planet. They would be islands of habitability inside a world that no longer supports open life. Every breath, every drop of water, and every harvest would depend on machinery, maintenance, and a stable supply of energy. A civilization confined to such systems would no longer live within a natural biosphere. It would carry a biosphere with it, enclosed and fragile, sustained by knowledge passed across generations. The deeper problem is that the sun's brightening does not stop. Underground shelters can soften surface heat, but they cannot prevent the planet as a whole from warming. As the oceans vanish and the atmosphere changes, even the crust becomes a less reliable refuge. Solar heat presses downward from above, while geothermal heat rises from below, narrowing the band in which temperatures remain tolerable. The Earth also loses many of the resources that make long-term survival easier. Water becomes difficult to obtain. Atmospheric gases must be manufactured or recovered. Agriculture can no longer depend on soil, rain, or seasons. A habitat may remain viable for thousands or even millions of years, but the stellar trend continues beyond the life of any single structure. Survival therefore begins to point outward. The solar system contains many worlds, and as the sun grows brighter, some regions now frozen receive more warmth. Mars lies farther from the sun and may briefly offer milder surface temperatures than it has today, though its thin atmosphere, low gravity, radiation exposure, and limited water remain severe obstacles. It is not a ready replacement for Earth. Any settlement there would still require extensive engineering, and the same brightening that first makes Mars warmer would eventually make it too hot. Farther out, icy moons orbit the giant planets. Beneath their surfaces, some already contain deep oceans kept liquid by tides and internal heat. As solar energy increases, their outer ice may thin, and regions once sealed in darkness may become more accessible. Moons around Jupiter and Saturn could pass through intervals when their surfaces or shallow interiors become less hostile. Yet these worlds also face intense radiation, weak sunlight in the earlier stages, complex chemistry, and low gravity. Their future habitability is temporary because the warming zone continues to move outward. No location within the solar system remains permanently safe from an aging sun. A civilization capable of surviving across such timescales must become mobile, adapting not to one new home but to a sequence of changing environments. It may inhabit planets, moons, asteroids, artificial stations, or vast structures built in space. Small bodies offer minerals and water ice without the deep gravity wells of planets. Rotating habitats could create an imitation of gravity through motion, while mirrors and shielding could regulate light and radiation. Inside them, temperature, atmosphere, and ecology would be designed rather than inherited. Their distance from the sun could change as the star brightens. At first, such habitats might remain near Earth or Mars. Later, they could migrate toward the outer planets and the colder reaches beyond them. In this future, the solar system becomes less a collection of fixed homes than a landscape through which life moves. The engineering required is immense, but the available time is also immense. The sun's changes unfold over hundreds of millions as billions of years. Civilizations, if they persist at all, do not need to complete the entire journey at once. They can expand step by step, learning to live beyond planets long before Earth becomes uninhabitable. The greatest uncertainty is not whether physical escape is imaginable, but whether intelligence and social continuity can survive long enough to attempt it. Species do not usually endure for billions of years. Civilizations are even more fragile. They face internal conflict, environmental damage, technological failure, impacts, disease, and changes that cannot be predicted from the present. The future beings that confront the aging sun may no longer be human in the modern biological sense. Evolution, genetic adaptation, artificial bodies, or forms of machine intelligence could alter what survival means. The descendants of Earth may require less water, tolerate more radiation, or live in environments that would be impossible for present organisms. Yet whatever their form, they remain dependent on ordered systems, usable energy, and the preservation of information. The movement away from Earth is therefore not only a journey through space, it is a transfer of memory, the chemistry of terrestrial life, the structure of ecosystems, and the accumulated knowledge of countless generations must be carried into places where none of those things arise naturally. The challenge grows greater as the sun approaches its red giant phase. Long before its outer layers expand toward Earth's orbit, its luminosity makes the inner solar system increasingly hostile. Habitats must move farther out or shield themselves behind enormous barriers. The giant planets and their moons receive levels of sunlight once found much closer to the sun. Frozen surfaces thaw, but the warming may be rapid on geological timescales. Ice turns to water and then to vapor. Atmospheres form and escape. Temporary environments appear and disappear. A moon may enjoy a brief interval of surface liquid water before continued heating destroys it. These passing windows could become stepping stones, but none offers a final refuge. The outer solar system also becomes disturbed as the sun loses mass during its later evolution. Weaker gravity allows planetary orbits to expand. Comets and smaller bodies may shift into new paths. Some objects are ejected, while others move inward. A civilization spread across many habitats would face not only heat, but a changing gravitational landscape. Stability would depend on constant observation and adjustment. Eventually, Survival within the solar system may require leaving it entirely. Interstellar travel is far more difficult than movement between planets. The nearest stars are separated by distances so large that even light takes years to cross them. Any slower craft must operate for generations, perhaps for centuries or longer. It must carry a closed ecological system or maintain life in some reduced state. It must survive dust impacts, radiation, mechanical failure, and the uncertainty of its destination. The target star must be chosen carefully, because stars also age, flare, and change. A smaller red dwarf can shine for far longer than the Sun, but many red dwarfs produce powerful magnetic activity, especially in their youth. A larger star offers more light but a shorter life. Planets may be absent, hostile, or already occupied by chemistry that complicates settlement. The search for a lasting home becomes a search not for perfection, but for time. Even successful migration cannot escape stellar evolution forever. Every star has a history. Some burn for millions of years, others for trillions, but none remains unchanged without limit. A civilization moving from star to star only postpones the larger cosmic problem. Yet postponement on such scales is not trivial. It can provide ages of continued existence, allowing life to spread far beyond the world where it began. The death of the Sun would then become a local event rather than the end of Earth's entire biological legacy. Long after the home planet is sterile, descendants of its biosphere might watch the Sun from distant habitats or from another planetary system. Its light would appear as one star among many, carrying no warmth across the intervening darkness. The Earth itself might remain as a known location, preserved in records, models, and inherited stories without dialogue or living witnesses on its surface. The migration outward changes the meaning of home. At first, home is a planet with oceans, air, and soil. Later, it is a sealed habitat. Later still, it may be a moving vessel between stars. The common element is not the ground beneath it, but the continuity of life within it. The Sun gives Earth enough time for intelligence to arise, and perhaps enough warning for that intelligence to leave. Whether the opportunity is used remains unknowable. The physics permits paths of escape, but physics does not guarantee that any civilization follows them. Across the distant future, the habitable zone continues its slow outward drift, and the descendants of Earth, if any remain, must drift with it until even the solar system itself becomes a place to leave behind. The Sun's transformation into a red giant begins when the long central supply of hydrogen finally becomes too depleted to support the star in its familiar form. For billions of years, fusion in the core has provided the outward pressure needed to resist gravity. Once that central fuel is largely exhausted, the balance changes. The helium-rich core can no longer produce enough energy through hydrogen fusion, so gravity gains ground and compresses it. The contraction raises the core's temperature, while hydrogen continues to burn in a shell surrounding the inert helium center. This shell produces energy at a faster rate than the old core once did. The Sun grows more luminous, and its outer layers respond by expanding. The change is not a sudden explosion. It is a prolonged swelling that carries the star into a different phase of existence. The surface moves outward across millions of kilometers, and as it spreads over a far greater area, its temperature falls. A cooler surface gives off redder light, even though the total energy flowing from the star becomes vastly greater. The Sun appears red not because it is weakening, but because its outer atmosphere has become enormous and relatively cool while the interior burns more fiercely than before. From a distant point in the solar system, the transformation would be unmistakable. The once compact yellow star would grow into a vast red presence, dominating the inner sky and shining with a luminosity many times higher than it has today. Mercury would experience the change first. Its surface, already scorched in the present era, would be heated beyond anything that could preserve its familiar form. As the Sun expands, the planet may be engulfed entirely. Venus follows in a region of rising heat and thinning orbital safety. Its dense atmosphere cannot protect it from the star's outer layers, whether it is swallowed directly or destroyed through intense heating and drag. Its future ends close to the swollen Sun. Earth lies farther out, but by this stage it has already been lifeless for ages. Its oceans are gone, its atmosphere altered or stripped, and its surface reduced to dry rock shaped by heat and radiation. The red giant phase does not begin Earth's destruction. It arrives after the biosphere has long vanished. What it threatens now is the planet's physical survival. The Sun's expansion is driven by the changing structure of the core. As the helium center contracts, the surrounding hydrogen-burning shell grows hotter and more productive. Energy pours outward through the stellar envelope. The outer layers expand because the increased energy flow supports them at greater distances from the center. As they rise, they become less dense and more weakly bound. The Sun's gravity still holds the star together, but the envelope becomes extended, turbulent, and vulnerable to mass loss. Powerful stellar winds begin carrying material into space. The Sun sheds atoms that once formed its outer layers, creating a widening cloud around the evolving star. This loss of mass affects the entire solar system. A star's gravity depends on its mass, so as the Sun becomes lighter, the orbits of surviving planets expand. Earth, if it remains intact, slowly moves farther away. That outward drift may seem like a possible escape from the swollen Sun, but the outcome is not simple. The expanding solar atmosphere can reach across Earth's orbit, and the thin gas surrounding the red giant may exert drag on the planet. Tidal forces between Earth and the enlarged Sun can also remove orbital energy. Mass loss pushes Earth outward, while drag and tides can pull it inward. The final result depends on the detailed rate of expansion, the amount of mass the Sun loses, and how strongly its outer layers interact with the planet. Models do not all produce exactly the same fate. Some allow Earth to move beyond the largest radius of the Sun. Others suggest that the planet spirals inward and is engulfed, even in the narrow possibility of physical escape. Earth remains a burned and airless remnant, its surface melted or transformed under extraordinary heat. Survival of the orbit would not mean survival of the world. During the red giant phase, the Sun's appearance also becomes less steady. The enormous outer envelope supports large convective motions, with hot material rising and cooler material sinking across regions far larger than the present solar surface. Pulsations may cause the star's radius and brightness to vary. Its atmosphere extends outward in layers that are difficult to define as a single sharp surface. The familiar photosphere gives way to a vast shifting boundary where gas thins gradually into space. The Sun is still held together by gravity, but it no longer resembles the stable star that once illuminated Earth. Its structure is looser, its winds stronger, and its energy output more variable. The inner planets exist inside an environment increasingly filled with stellar material. Dust can form in cooler regions of the outflow, and gas streams away to become part of the surrounding interstellar medium. The Sun begins returning matter to the galaxy long before its luminous life is over. The red giant is therefore both a dying star and a source of future material. Atoms once locked inside the Sun are released into space, where they may eventually mix with distant clouds and become part of new stars or planets. The transformation also moves the habitable zone far beyond its present location. regions around the giant planets receive levels of light once found nearer Earth. Icy surfaces warm, and some frozen reservoirs may melt or evaporate. For a brief interval, worlds that spent most of solar history in deep cold may pass through milder conditions. Yet the red giant's evolution is too unstable and too short-lived to provide a lasting sanctuary. Any temporary oceans or atmospheres formed in the outer solar system face continued heating, strong radiation, and later cooling as the sun sheds its envelope. Habitability sweeps outward like a passing tide, touching distant worlds before moving on. Beneath the giant's outer layers, the core continues to contract toward a more dramatic threshold. Helium remains unable to fuse efficiently until the temperature rises high enough. Because the core is extremely dense, its matter behaves in a way unlike ordinary gas. The pressure that supports it becomes partly controlled by quantum effects rather than temperature alone. Electrons are forced into a crowded state that resists further compression. This condition, known as electron degeneracy, allows the core to become hotter without expanding in the usual way. In an ordinary gas, rising temperature produces expansion, which cools the material and regulates the reaction rate. In the degenerate helium core, that safety response is weakened. The temperature climbs toward the point where helium nuclei can begin to combine. When fusion finally starts, the reaction rate increases rapidly because the dense core cannot immediately expand and cool. A powerful burst of helium fusion follows, known as the helium flash. Most of its energy remains trapped inside the star and does not tear the sun apart. From outside, the event is far less dramatic than its name suggests. Inside, however, it changes the core's condition. The energy lifts the degeneracy, allowing the core to expand and settle into a new balance. The sun then contracts somewhat from its greatest red giant size and begins a shorter period of relative stability, powered by helium fusion in the center and hydrogen fusion in a surrounding shell. The red giant phase is therefore not a simple final swelling followed immediately by darkness. It contains transitions, contractions, renewed balances, and later expansions. The sun repeatedly reorganizes itself as different fuels become available under different pressures and temperatures. Each new stage is shorter than the one before because hotter fusion reactions consume fuel more rapidly. The long calm of hydrogen burning gives way to a faster and more complicated old age. The star that once changed almost imperceptibly across geological eras now evolves with increasing urgency. Its outer appearance grows vast while its inner future narrows. Carbon and oxygen begin to form in the core as helium nuclei combine, building the dense remnant that will eventually remain after the outer layers are gone. Around that core, the swollen envelope continues to pulse, churn, and escape. The red giant is not yet the sun's final state, but it is the moment when the familiar star disappears. Its scale expands beyond the old planetary order, its light becomes deeper in color, and its gravity begins releasing its hold on the material that once formed its surface. The solar system enters its last great transformation under a star that has become immense, unstable, and brilliant, while the small worlds nearest it face the final consequences of having formed too close to a changing sun. Earth's final fate during the sun's red giant phase remains one of the most uncertain parts of the solar future, not because the broad danger is unclear, but because several immense forces act at the same time and in opposite directions. Long before the sun reaches its greatest size, Earth is already lifeless, dry, and transformed by heat. The question is no longer whether the planet remains habitable. That possibility has ended ages earlier. The remaining question is whether the physical body of Earth survives at all. As the sun swells, it loses mass through increasingly powerful stellar winds. Gas once held in the outer layers escapes into space, reducing the gravity that binds the planets to the star. With less solar mass at the center, planetary orbits tend to expand. Earth is pushed outward, moving into a wider path that may carry it away from the most extended layers of the giant Sun. This outward migration offers the narrow possibility that the planet avoids direct engulfment. Yet the same enlarged Sun creates forces that work against that escape. Its outer atmosphere becomes vast, thin, and difficult to define. Even if the visible surface does not extend fully to Earth's widened orbit, tenuous gas may reach the planet. As Earth moves through that material, drag removes orbital energy. The effect is extremely small at first, but the red giant phase lasts long enough for small losses to accumulate. Tidal interactions also grow stronger. The swollen Sun raises tides on Earth, while Earth raises a tiny distortion on the Sun. These gravitational distortions exchange energy and angular momentum between the planet's orbit and the star's rotation. Because the giant Sun rotates slowly, tides can drain energy from Earth's path and pull the planet inward. Mass loss urges Earth outward. Drag and tides draw it back. The outcome depends on which influence dominates at each stage. That balance is sensitive to details that are difficult to model with complete certainty, including the rate at which the Sun loses mass, the depth and density of its outer atmosphere, the efficiency of tidal dissipation, and the exact maximum radius reached during the largest expansions. Small differences in these values can separate escape from engulfment. If Earth is drawn into the solar envelope, its end is not likely to resemble a solid planet falling through a sharp wall of flame. The boundary of the red giant is diffuse. Earth enters increasingly dense layers of hot plasma while still orbiting the core. Friction rises, the planet loses speed and spirals deeper. Its surface, already heated beyond the melting points of common rock, becomes a global ocean of magma. Minerals vaporize into a heavy atmosphere of rock vapor. The remaining structure is battered by heat, pressure, and collisions with solar particles. As the planet descends, drag grows stronger, shortening the orbit more rapidly. Earth may be stripped layer by layer. The crust and mantle evaporate into the surrounding star, and even the dense metallic core eventually dissolves or is torn apart. The atoms that once formed oceans, continents, living cells, cities, and machines become mixed into the Sun's convective envelope. In that ending, Earth does not explode as a single object, it is absorbed. Its material joins the star that created the conditions for its formation and later erased them. If Earth instead moves beyond the Sun's maximum reach, the escape is only geometric. The planet does not preserve anything like its present identity at the surface. Intense radiation heats the crust until wide regions melt. The atmosphere, if any portion remains, is blasted away or converted into vapor rich in material released from the rocks below. Mountain ranges soften and collapse into magma. Ancient ocean basins lose their meaning beneath a mobile surface. The planet may glow from its own heat, not with life or fire, but with molten stone. As the Sun later sheds its outer layers and contracts, Earth begins to cool again. A new crust could eventually form over the melted exterior. It would be a crust without oceans, breathable air, or ecosystems, marked by chemistry altered under red giant temperatures. The surviving world would be less a preserved Earth than a planetary remnant carrying the mass and orbit of the old planet. Its rocks might still contain faint isotopic traces of earlier ages, but most surface evidence of life would be erased, melted, buried, or dispersed into space. The Moon shares this danger, though its future is linked to Earth's changing orbit and to the Sun's mass loss. As solar gravity weakens, Earth's path expands, but the relationship between Earth and Moon also evolves. Tidal interactions have long pushed the Moon slowly outward from Earth. Across billions of years, that separation grows, while Earth's rotation slows. Before the red giant reaches its largest size, the pair may occupy a very different configuration from the present. Solar tides become more influential as the Sun expands, and the weakening gravitational structure of the system can destabilize the lunar orbit. The Moon may remain bound, move into a wider path, collide with Earth, or escape into an independent orbit around the Sun. The exact result is uncertain, but none of the possibilities preserves the familiar night sky. If Earth is engulfed, the Moon is likely engulfed as well or disrupted nearby. If Earth escapes, the Moon may survive as another scorched body or may be lost during the gravitational upheaval. The inner solar system as a whole becomes a place of disappearance and rearrangement. Mercury is almost certainly consumed. Venus faces a similarly severe fate. Asteroids are heated, altered, or pushed into new orbits. Some bodies fall inward. Others migrate outward as the Sun loses mass. Comets from distant reservoirs may be disturbed and sent across the system. The orderly architecture that persisted through most of solar history becomes less secure. This instability does not mean every orbit immediately turns chaotic, but the relationships among the surviving bodies are rewritten by the changing mass and size of the central star. Earth's fate must therefore be understood as part of a larger gravitational transition. The Sun is no longer merely brighter. It is becoming lighter while occupying a vastly greater volume. Its influence changes in two opposite ways. Its gravity weakens because mass is being lost, while its physical atmosphere reaches farther into the planetary system. The planets respond not to one smooth transformation, but to a sequence of expansions, contractions, pulses, and winds. During some phases, Earth may move outward. During others, tidal forces may dominate. The final approach to engulfment, if it occurs, could be decided only near the Sun's greatest radius. For any distant observer, the event would unfold slowly. Earth would not vanish in an instant. Its orbit would tighten over many revolutions, each passage carrying it through denser gas. The planet would leave a wake in the solar envelope, transferring energy to the surrounding material. That energy could help push some gas outward, while the orbit continued to decay. Eventually, the distinction between planet and star would disappear. If Earth remained outside, the observer would instead see a dark or glowing point moving around a giant red disk, close enough to destruction that survival depended on a margin small beside the scale of the star. Scientific caution remains essential because red giant envelopes are complex. Stellar winds are irregular, magnetic fields, convection, pulsation, and dust formation all influence how mass leaves the star. Tidal effects depend on processes inside the convective envelope that are still modelled with uncertainty. The future Sun cannot be observed directly. But other red giants provide examples of similar evolution. Some giant stars appear to retain closely planets. Others show signs that planets have been consumed, perhaps altering the star's rotation or chemical composition. These systems reveal that both survival and engulfment are possible, depending on mass, distance, and timing. Earth lies near a dangerous boundary. Its position is not safely distant, yet solar mass loss may enlarge its orbit enough to create uncertainty. That uncertainty does not offer hope for life, only ambiguity about the preservation of stone, whether swallowed or spared. Earth's role as a living world ends long before the decision is made. The red giant phase settles only the last physical question. One outcome returns the planet's material to the Sun. The other leaves a scorched remnant circling the exposed core that follows. In either case, the familiar Earth is gone, and the orbit that once carried a blue world through gentle sunlight becomes either a path into the star or a silent track around its dying remains. After the helium flash, the Sun enters a quieter interval that almost resembles a second Middle Age, though the resemblance is deceptive. The violent ignition in the degenerate core releases enough energy to change the structure of the star, lifting the quantum pressure that had prevented ordinary expansion. The core swells slightly and cools. The surrounding layers contract, and the Sun becomes smaller and less luminous than it was at the peak of the first red giant phase. It has not returned to its former state. The outer planets still orbit a star transformed by immense mass loss. The inner worlds are damaged or gone, and the centre now burns a fuel that was once merely the ash of hydrogen fusion. Helium nuclei combine through a sequence known as the triple alpha process. Two helium nuclei briefly form an unstable beryllium nucleus, and before it can fall apart, a third helium nucleus joins it to create carbon. Some of that carbon captures another helium nucleus and becomes oxygen. In this way, the Sun begins making the elements that form much of the solid structure of planets and living bodies. Carbon and oxygen are not produced as a symbolic final gift. They emerge because the core has become hot and dense enough for helium fusion, and because the laws of nuclear physics allow these reactions to proceed. The future white dwarf will be built mainly from these two elements, the compact residue of this brief central furnace. Helium burning gives the Sun a new source of outward pressure. For a time, the star settles into equilibrium again. Helium fuses in the core, while hydrogen continues to fuse in a shell farther out. This layered arrangement produces a steadier structure than the one that preceded the helium flash. The Sun occupies a stage astronomers associate with stars that have moved away from the upper red giant branch and entered a more compact phase. Its exact brightness and temperature change, but the larger meaning is clear. A new fuel has been found, and the crisis of the contracting helium core is temporarily resolved. Yet the new stability is short compared with the long age of hydrogen burning. Helium releases less usable energy per unit mass than hydrogen, and the hotter core consumes it rapidly. The Sun's first stable life lasts for billions of years. Its central helium-burning life endures only for a small fraction of that span. The star has entered an era in which each successive stage passes more quickly than the one before. The reason is not simply that less fuel remains. Higher temperatures accelerate nuclear reactions, and each new fuel requires more extreme conditions. The star responds to exhaustion with contraction. Contraction creates heat, and heat opens a new reaction pathway. But every pathway yields a smaller return before the core changes again. During helium burning, the Sun's interior becomes more sharply divided. At the center, carbon and oxygen accumulate as helium is consumed. Around the core, helium continues to burn where conditions permit, and beyond that, a shell of hydrogen fusion adds fresh helium to the layers below. The star resembles a structure built from nested furnaces, each one operating at a different depth. Energy moves outward through dense matter, then through the enormous convective envelope, where rising and sinking plasma carries heat toward the surface. Convection dredges material from deeper layers and mixes it into the atmosphere. The surface composition changes as products from nuclear processing become more visible. The Sun's spectrum would reveal that its outer layers no longer have exactly the same chemical pattern they displayed during the long main sequence. In the solar system around it, there is no living Earth to witness this shift. Any surviving descendants of terrestrial life must observe from distant habitats, outer worlds, or another star. To them, the Sun is a brilliant red or orange object whose light carries the signature of a furnace, now producing carbon and oxygen. The same star remains at the center, yet its radius, mass, color, and energy source have all changed. The helium burning stage also exposes the limits imposed by the Sun's mass. Stars much more massive than the Sun continue beyond carbon and oxygen, compressing their cores until they fuse heavier elements in a sequence that can reach iron. Their final collapse may produce a supernova, scattering newly formed material across space. The Sun cannot follow that path. Its gravity is not strong enough to drive the carbon and oxygen core to the temperatures required for sustained carbon fusion. Once helium is exhausted, no new central fuel can take over. This limit determines the character of the Sun's death. It will not end in a catastrophic core collapse. It will shed its outer layers and leave the unfused carbon and oxygen core behind as a white dwarf. During helium's brief reign, however, that ending is not yet visible from the surface. The star still shines through active fusion and maintains a broad envelope. The core gradually becomes richer in carbon and oxygen, while the amount of helium at the center falls. Just as hydrogen exhaustion once altered the balance, helium exhaustion eventually does the same. The central fusion rate declines. Gravity compresses the core again, but this time contraction cannot raise the temperature enough to ignite the carbon. Electron degeneracy returns as the carbon and oxygen matter becomes extremely dense. The core stops behaving like an ordinary hot gas and becomes a compact object supported increasingly by quantum pressure. Around it, fusion does not cease. Helium burns in a shell just outside the inert core, while hydrogen burns in another shell above that. These two shells do not always operate smoothly. Their energy output rises and falls, and the star begins entering a more unstable phase. Before that instability becomes dominant, the end of central helium fusion carries a quiet finality. For the second time, the Sun exhausts the fuel at its center. The first exhaustion opened the path to helium. The second opens no comparable path beyond it. The sequence of usable central fuels ends here. Carbon and oxygen remain, but the star cannot unlock their stored nuclear energy through ordinary fusion. The core contracts and heats, yet the threshold for carbon burning stays out of reach. The Sun has reached the limit set by its birth mass, a limit established before planets formed and before Earth existed. That original mass determined the pressure available in the core, the fuels the star could ignite, and the kind of remnant it would become. This gives the helium-burning era a strange position in the Sun's life. It is both a renewal and a farewell. Fusion continues, balance returns, and new elements are made, but the star is using its final central fuel. The carbon and oxygen accumulating in the core are not stepping stones toward another long age. They are the substance of the remnant. Every helium nucleus fused narrows the remaining time. The Sun shines because it is building the object that will survive after the shining ends. Across this interval, the surrounding planetary system continues to adjust to the reduced solar mass. Orbits widen. Distant icy bodies receive warmth from the enlarged star, though the period of relative calm is too brief to create a lasting new biosphere without deliberate intervention. The second giant phase will be more unstable than the first. The star will pulse, shed matter, and lose the envelope that still conceals its dense core. Helium burning delays that event, but it also prepares it by increasing the carbon and oxygen mass at the center and by changing the arrangement of the surrounding fusion shells. As the last central helium disappears, the core becomes silent in the nuclear sense. It still radiates heat and contracts under gravity, but it no longer generates energy through fusion. The luminous activity moves outward into shells, making the envelope swell once more. The Sun begins climbing toward its final giant form, larger, cooler at the surface and increasingly unstable. The era of helium closes without an explosion. Its end is a shift in where energy is made and in what can still burn. At the center remains a dense sphere of carbon and oxygen, no larger than a small fraction of the star's swollen body, yet containing most of the meaning of what follows. Around it, thin shells continue their work. Above them, the vast envelope trembles. The sun has found no third life. Its last central flame has passed, and the star now moves toward the moment when its outer layers can no longer remain attached. After central helium fusion ends, the sun enters the most unstable period of its life. At the center lies a dense core of carbon and oxygen that cannot become hot enough to ignite sustained carbon fusion. Around it, two thin shells continue producing energy. Helium burns close to the core, while hydrogen burns farther out. These shells do not remain perfectly steady. Their rates rise and fall, and the star responds with repeated expansions, contractions, and violent pulses. The sun has become an aging structure with its active furnaces pushed away from the center, and every pulse loosens the enormous envelope surrounding the core. The outer layers swell to vast distances, cool, and become only weakly bound by gravity. Material that once remained secure inside the star begins to escape. The sun sheds its skin through powerful winds that carry gas and dust into space, slowly revealing the compact remnant hidden beneath. This phase belongs to a class of old stars known as asymptotic giant branch stars. The sun becomes a giant for the second time, larger and more unstable than before. Its surface may extend far into the region once occupied by the inner planets. Convection cells grow to enormous size, lifting hot matter from deep layers and allowing cooler material to sink. These pulsations help push material away from the surface. In the cool outer regions, atoms combine into molecules, and tiny grains of dust begin to form. Radiation from the star presses against those grains. The dust drags surrounding gas with it, turning the stellar atmosphere into a persistent outflow. Later, it becomes a super wind, removing the envelope at an extraordinary rate by stellar standards. The sun can lose a substantial fraction of its remaining mass during this final giant stage. Its gravity weakens further, and the orbits of any surviving planets widen. Distant objects drift into larger paths. While some loosely bound comets and small bodies may escape the solar system entirely, the architecture formed around the young sun is being dismantled by the old one. Yet the most important change occurs within the star itself. The helium-burning shell surrounding the inert carbon and oxygen core gradually consumes helium and produces more carbon and oxygen. As it burns, it deposits additional material onto the core, increasing its mass and compression. The helium shell is thin and highly sensitive to temperature. A slight rise in temperature makes fusion proceed much faster, releasing a burst of energy. The shell expands and cools, causing the reaction to weaken. It later contracts and heats again. This cycle produces thermal pulses, brief episodes during which the sun's internal energy output rises dramatically. The hydrogen-burning shell may temporarily shut down while the helium pulse dominates, then restart after the star settles. Each pulse is followed by a period of relative calm, but the calm does not restore the star. The envelope is thinner, the core is heavier, and more material has been sent into space. These pulses also stir the sun's chemical layers. Convection can reach inward after a pulse and carry newly made carbon toward the surface. This process, called dredge-up, changes the composition of the outer atmosphere. Elements created or altered in the interior become visible in the star's spectrum and are eventually released into the surrounding cloud. The sun is not massive enough to manufacture the full range of heavy elements made in larger stars and supernova. but its final winds still enrich space with carbon, nitrogen, oxygen, and other material processed during its life. Some heavier nuclei can also form when atomic nuclei capture neutrons slowly over time. These products are carried outward with the escaping envelope. In this way, the dying sun contributes to the chemical evolution of the galaxy. The matter it releases may drift for millions of years before mixing with interstellar clouds. Much later, portions of those clouds may collapse into new stars and planets. Atoms once inside the sun could become part of another planetary system, another atmosphere, or forms of chemistry that have no connection to Earth. The sun's death is therefore not the disappearance of its substance. It is a redistribution. The central core remains, while the outer star spreads into the galaxy. From a great distance, the escaping material begins as an irregular cocoon around the red giant. The outflow is not always perfectly spherical. Magnetic fields, rotation, pulsations, companion objects, if any, remain nearby, and the presence of planets or smaller bodies can shape the gas. Dense regions form arcs, rings, clumps, or opposing lobes. The precise shape of the sun's final nebula cannot be known with certainty. A single star may produce a more rounded shell, while interactions with planets could create a symmetry. Whatever form develops, the cloud expands far beyond the old scale of the planetary system. It carries the sun's outer layers into a widening region of darkness, where the gas becomes thinner with every passing age. While the envelope escapes, the hidden core grows increasingly exposed. It is extraordinarily hot because it contains the compressed thermal history of the star, yet it is no longer producing energy through sustained fusion. Electron degeneracy pressure supports it against further collapse. This pressure arises because electrons cannot all occupy the same quantum states. When matter is compressed to extreme density, the crowded electrons resist being forced closer together. The core can therefore remain stable without the temperature-dependent pressure that supported the sun during its active life. Its mass is packed into a sphere roughly comparable in size to Earth. Though its density is far beyond anything found in an ordinary planet, for most of the final giant phase, this core remains buried beneath the bright envelope. As mass loss accelerates, the covering layers become too thin to maintain the star's giant appearance. The red surface begins to contract away, not because the core draws the envelope back, but because the envelope is leaving. The star moves toward a transition in which the hot core can shine directly upon the gas it has expelled. Ultraviolet radiation floods the surrounding cloud, stripping electrons from atoms and causing the gas to glow. This illuminated shell is known as a planetary nebula, though it has nothing to do with planets. The term survives from early telescopic observations, when some of these round, hazy objects resemble distant planetary disks. In reality, each is the brief luminous farewell of a star similar in mass to the Sun. The nebula phase is visually magnificent but short. The cloud expands rapidly, and as it spreads, its density falls. The central core also begins cooling. After only a small interval compared with the Sun's total life, the gas becomes too thin, and the core too faint to keep the nebula brightly ionized. The colours fade into the interstellar background. Before that fading, however, the dying sun may create one of the most delicate structures in the sky. Oxygen can glow in green or blue tones, hydrogen in red, and other elements in their own characteristic light. These colours arise from atoms absorbing energy and releasing it at specific wavelengths. They reveal the composition and motion of the ejected material. Shells from different pulses may overlap, showing that the envelope did not leave in one smooth event. The nebula records the rhythm of the sun's final instability. each arc marking a stage in the loss of the star's outer body. No explosion tears the sun apart, its ending is slower and more layered. Wind follows pulse, pulse follows contraction. And the envelope becomes less massive until gravity can no longer keep it near the core. The sun dies by letting go. Most of the star that once filled the sky from Earth becomes a cloud expanding through space. Only the dense carbon and oxygen center remains behind. The transition separates two kinds of existence. Before it, the sun is still a star powered by active fusion in shells. After it, the remaining object shines only because it is hot. The shedding of the envelope is therefore the true end of the sun as a fusion-powered star. Its outer material departs carrying traces of every major stage that came before, from the hydrogen of the original molecular cloud to the carbon made during helium burning. The core emerges small, brilliant, and exposed, surrounded for a short while by the glowing remains of its former self. Then the cloud moves outward, the old planetary system widens and empties, and the white dwarf is left alone at the center of a greatly altered darkness. When the sun's outer layers have drifted away, the object left at the center is no longer a star in the ordinary sense. It produces no new energy through sustained fusion, yet it shines with fierce intensity because the exposed core is still extraordinarily hot. This remnant is a white dwarf, a sphere roughly comparable in size to Earth, but containing a large fraction of the sun's original mass. Its density is so extreme that a small volume of its matter would outweigh mountains of ordinary rock. The atoms inside are crushed into a state where nuclei are packed closely together and electrons move through the material under conditions set by quantum mechanics. Gravity still pulls inward, but the white dwarf does not continue collapsing because electron degeneracy pressure resists further compression. This support is not created by heat and does not fade in the same way as ordinary gas pressure. It arises from the rule that identical electrons cannot all occupy the same quantum state. As gravity forces matter into a smaller volume, the electrons are driven into increasingly energetic states, creating a pressure that holds the remnant up. The sun has therefore reached a form of balance, unlike the one that sustained it during its long life. Once, fusion provided energy and heat helped resist gravity. Now, no central furnace remains. The core survives because matter itself refuses to be compressed beyond a certain point. The newborn white dwarf is far hotter than the present sun's visible surface. Its ultraviolet radiation floods the surrounding planetary nebula, causing the expanding gas to glow. For a brief time, the remnant appears as the brilliant center of a delicate shell made from the sun's former envelope. The giant star that once stretched across the inner solar system has been reduced to an object no larger than a planet, while most of its outer mass is scattered through an expanding cloud. Yet the small core can still outshine many ordinary stars at certain wavelengths because its surface is so hot. This phase cannot last. The white dwarf has only stored thermal energy, and every photon it releases carries part of that energy away. There is no fusion to replace the loss. The remnant begins a cooling process that continues for spans far greater than the active life of the sun. At first, the change is relatively rapid because the temperature difference between the white dwarf and surrounding space is enormous. Later, as the remnant cools, the energy escapes more slowly. The path toward darkness stretches across almost unimaginable ages. Inside the white dwarf, carbon and oxygen dominate, formed during the sun's helium-burning stage. These nuclei exist within a dense sea of electrons. The matter is not arranged like familiar solid rock, liquid metal, or ordinary gas. At first, the interior remains so hot that the nuclei move freely through the compressed material. As cooling continues, their motion slows. Eventually, the carbon and oxygen nuclei begin settling into an ordered lattice, a process often described as crystallization. The white dwarf becomes solid from the center outward. Though this solidity exists under pressures unlike anything found on Earth, crystallization releases stored energy and delays the cooling, adding another long chapter to the remnant's fading life. The sun's core may gradually become a vast crystalline sphere, not a transparent jewel in the ordinary sense, but an ordered structure of carbon and oxygen nuclei immersed in degenerate electrons. Around the white dwarf, the planetary nebula does not remain. Its gas expands, thins, and merges with the interstellar medium. Soon, the bright shell becomes too diffuse to see. The atoms once held in the sun's surface travel outward at different speeds and in different directions. Some mix with nearby clouds. Some drift through the galaxy for ages before joining new structures. The remnant at the center becomes increasingly isolated. If any planets survive, their orbits are wider than before because the sun has lost so much mass. Giant planets may continue circling at expanded distances. Their moons persist in altered light, receiving only the faint glow of the white dwarf. Small bodies and comets may occupy unstable paths, and some are scattered away. Others fall inward. The system becomes a dim collection of remnants orbiting a stellar corpse. A surviving Earth, if it escaped engulfment, would move through this darkness as a burned and frozen world. After the intense heat of the red giant phase, its surface would gradually cool, molten rock would harden. Any temporary atmosphere of vaporized minerals would condense or escape. The planet might eventually become colder than the Earth of the present, because the white dwarf's luminosity steadily declines. No oceans return, no biosphere reappears. The water lost to space remains lost, and the chemical and thermal violence of the giant phases has erased the conditions that once supported life. The white dwarf itself may briefly create a new habitable zone very close to its surface, where the reduced light could allow moderate temperatures on a tightly orbiting world. Yet such a region would move inward as the remnant cools, and any planet close enough to benefit would have faced the star's earlier expansion and mass loss. New planets might form from debris or migrate inward through later interactions, but these possibilities are uncertain and would not restore the old solar system. The white dwarf stage is defined less by new beginnings than by endurance. Its existence is stable because the sun's mass remains below the limit at which electron degeneracy pressure would fail. A more massive white dwarf can be forced toward collapse if it gains enough matter from a companion star, but the sun has no nearby stellar companion to feed it, left alone. It does not explode as a supernova, it simply cools. Its atmosphere, made of the lighter elements that float above the denser interior, may contain hydrogen or helium. These outer layers influence how heat escapes and how the remnant's spectrum appears. Over time, heavier elements sink under the intense gravity unless fresh material falls onto the surface. Asteroids or comet fragments disturbed from surviving orbits may occasionally strike the white dwarf, adding traces of rock-forming elements to its atmosphere. Astronomers observing other white dwarfs already detect such pollution, revealing the remains of planetary systems long after their stars have died. The future sun may carry similar evidence. Its light could briefly show calcium, magnesium, iron, or other elements from the shattered remnants of planets. In this way, the white dwarf may become an archive of destruction. The material falling onto it would contain fragments of worlds formed around the young sun, perhaps including pieces of bodies that once carried water or organic chemistry. As the white dwarf cools, its color changes. It begins blue-white because of its high temperature, then shifts toward white, yellow, orange, and red as the surface loses heat. The process is extraordinarily slow. The universe in its current age is not old enough for any white dwarf to have cooled completely. Every known white dwarf still retains some measurable warmth from the star it once was. The final theoretical state is called a black dwarf, an object so cold and faint that it releases almost no visible light. No black dwarfs exist yet because the cosmos has not had enough time to make them. The future sun must wait through periods vastly longer than its entire active lifetime before reaching that condition. During those ages, galaxies themselves change. Star formation declines as gas is consumed or dispersed. Existing stars burn out according to their masses. Red dwarfs continue shining long after larger stars are gone, while white dwarfs accumulate as quiet remnants. The sun becomes one among countless cooling cores scattered through an aging galaxy. Its once brilliant planetary nebula is forgotten in the interstellar medium, and its former planets move through widening darkness. The white dwarf remains compact, stable, and patient. It no longer controls climates or drives photosynthesis. It no longer sends a warm spectrum across oceans or casts familiar shadows across continents. Its influence is reduced to gravity and fading heat. Yet this small remnant is still the sun in physical continuity. It contains matter forged in the core, compressed by the final stages of stellar evolution, and preserved after the envelope has gone. The star's long history is condensed into an Earth-sized sphere of carbon, oxygen, and degenerate electrons. Birth cloud, main sequence, red giant, helium furnace, and planetary nebula all lead to this final luminous object. The sun does not disappear when fusion ends. It contracts into memory, glowing less with every age, while the solar system around it becomes a colder and quieter place. Long after the planetary nebula has faded into the interstellar medium, the remnant sun continues to cool in a darkness almost beyond ordinary imagination. The white dwarf still contains heat left from the star's active life, but no fusion replaces what radiates away. Its surface grows dimmer, its color shifts toward red, and the surrounding solar system receives less energy with every passing age. Any surviving planets move through orbits enlarged by the mass the sun lost during its final giant phases. Their surfaces freeze. Atmospheres collapse onto the ground or escape. Moons become hard, silent bodies beneath skies where the central light has weakened to a distant ember. The solar system is no longer organized around warmth. It is held together mainly by gravity, a collection of remnants circling a compact core that remembers the sun's former mass, but none of its former radiance. The white dwarf's cooling does not proceed at a constant rate. Early in its remnant life, heat escapes relatively quickly because the temperature difference between the star and space is large. Later, the process slows, the interior crystallizes, releasing latent heat and delaying the fall toward darkness. Carbon and oxygen nuclei settle into an ordered lattice, while electrons remain in a degenerate state, supporting the object against gravity. Over immense intervals, the white dwarf becomes increasingly solid, its remaining thermal motion fading through a sequence of changes that no civilization could witness from beginning to end. The universe itself is not yet old enough to contain the final product of this cooling. Every white dwarf observed in the present cosmos still glows to some degree. A black dwarf, the theoretical endpoint, requires far more time than has passed since the beginning of cosmic history. It would not be black in the sense of absorbing all light, but in the sense of producing almost none of its own. It would be a cold, compact sphere of crystallized matter nearly invisible except through its gravity or through the rare light it reflects. The future sun is expected to approach that condition only after spans measured not in billions, but in numbers of years so vast that familiar comparisons lose meaning. By then, the galaxy around it will also be changed. Most bright stars will have ended their lives. Massive stars disappear first because they consume fuel quickly. Stars like the Sun follow. Small red dwarfs persist far longer, burning hydrogen with extraordinary efficiency, but even they eventually exhaust their fuel. As the ages pass, the Milky Way becomes populated increasingly by stellar remnants, white dwarfs, neutron stars, black holes, and cold planetary bodies. Star formation declines as usable gas is locked into remnants, dispersed, or prevented from collapsing into new suns. The galaxy's spiral structure fades as the luminous stars that trace it vanish. What remains is a darker system shaped by slow gravitational encounters. The Sun's remnant does not necessarily stay forever with the same planetary companions. Over enormous periods, repeated gravitational interactions can alter orbits. Passing stars, compact remnants, or molecular clouds can disturb distant objects. Weak encounters accumulate. Some planets may be ejected into interstellar space. Others may fall inward toward the black dwarf or collide with one another. The most distant comets are especially vulnerable because they are only loosely bound. The solar system may gradually dissolve, not through a single catastrophe, but through the patient action of gravity across deep time. A surviving Earth remnant could wander alone through the galaxy after being released from the Sun, or it could remain in orbit until another encounter changes its path. If Earth was engulfed during the red giant phase, even that possibility is absent. Its atoms are already divided between the white dwarf and the material scattered into space. In either case, the original arrangement of planets does not remain permanent. The ordered system born from a disk around the young Sun eventually becomes a dispersed family of relics. Some of its matter joins the galaxy. Some stays locked in cold worlds. Some falls onto the central remnant, briefly releasing energy as impacts heat the surface. These flashes would be small and temporary against the long dark age. The black dwarf itself may not remain unchanged forever, though the answer depends on physics that has not yet been settled. Some theories propose that protons, the particles found in atomic nuclei, may eventually decay. No such decay has ever been observed, and experiments have only established that protons must survive for extraordinarily long periods if they decay at all. If proton decay is possible, the matter inside planets, white dwarfs, and other remnants slowly disappears into lighter particles and radiation. The future Sun would then erode from within across ages vastly longer than its cooling time. Its carbon and oxygen nuclei would not remain eternal. The black dwarf would lose mass particle by particle until little or nothing of the original star remained. If protons are perfectly stable, the remnant could survive much longer. Its future would then be controlled by rarer gravitational or quantum processes, collisions, and the changing structure of the universe. The distinction lies beyond current observation, and any description of that era must remain cautious. Known stellar evolution leads confidently to the white dwarf. The black dwarf follows from established cooling physics. What happens after that reaches into domains where direct evidence is limited and theoretical possibilities diverge. Even without proton decay, a cold remnant can still be affected by gravity. Galaxies evolve through encounters, mergers, and the gradual redistribution of energy among their members. Some objects gain speed and escape. Others lose energy and fall towards central black holes. Over enough time, the Sun's remnant might be ejected from the fading Milky Way, becoming a solitary object in intergalactic space. It might instead drift inward through repeated interactions and eventually approach a massive black hole. If captured, it would be torn apart or swallowed, its remaining mass joining an object far larger and darker. Neither outcome is certain for one particular remnant. Deep time magnifies tiny probabilities until events once considered unlikely become possible. The future solar system therefore has no single guaranteed final arrangement. It has a range of endings governed by the slow statistics of gravity. Meanwhile, the larger universe continues to expand. Distant galaxies recede, and over sufficiently long ages many pass beyond any region from which their light can reach the local remnants. The observable cosmos from the Sun's former location becomes emptier. Nearby gravitationally bound objects may remain together, but the wider universe fades from view. If cosmic expansion continues to accelerate as present evidence suggests, isolated groups of remnants become separated by growing darkness. The black dwarf sun, should it still exist, would inhabit a universe with little visible connection to the rich cosmic web that surrounded its birth. The atoms inside it, once formed in earlier generations of stars, gathered into a molecular cloud and became part of a new sun. That sun illuminated planets, supported life, expanded into a giant, and exposed its core. Now the same material rests in near darkness while the universe moves into an era dominated by remnants and empty space. There is no final moment when the sun's story clearly ends. Its fusion ceases first, its nebula fades later, its white dwarf cools across far longer ages, its planets disperse on uncertain timescales. Its remaining matter may persist, decay, escape, collide, or fall into another object. Death, at this scale, is not a point but a sequence of diminishing influence. The sun stops producing energy, then stops producing visible light, then perhaps loses even the structure that once held its matter together. What comes after the sun is therefore not a single object or event, it is a widening aftermath. The star's outer atoms mix with the galaxy. Its core becomes a white dwarf, then a black dwarf in the remote future. The worlds around it freeze, scatter, or vanish. The light that once sustained oceans and forests becomes a memory written only in the arrangement of matter and in any descendants of Earth that may have escaped. If life reaches other stars, the sun's death does not end its biological legacy. The chemistry and information shaped under its light continue elsewhere, separated from the remnant that made their origin possible, if nothing survives. The physical traces still endure for a time-altered planets, dispersed gas, and a cooling core moving through the galaxy. Eventually, even those traces become difficult to distinguish from the ancient material of the cosmos. The sun begins as a gathering of hydrogen in darkness and may end as darkness again. But the interval between those states changes a planetary system and gives life a temporary place within the universe. Its final future is not an explosion, nor a sudden disappearance, but an almost endless fading, each stage quieter than the last, until the star that once filled every earthly day becomes a cold and nearly invisible relic drifting through deep time,